Lab 5, Faraday's Law. The goals of this lab were to collect data of a magnet falling through a conductive tube of aluminum foil, to understand the relationship between a time-varying magnetic field to a curly electric field, to demonstrate force on a falling magnet due to an induced current loop, and then to create a computational model to model this magnet-tube interaction. There's some fundamentals we need to understand before going through with this lab. First, there's magnetic flux, the measure of a magnetic field that passes through a given area. Whenever flux changes, a magnetic field is induced. Next is Faraday's law. This connects magnetic and electric field. A time-varying magnetic field induces a voltage with a magnitude equal to the magnetic flux. Next is Lenz's law. This tells us the direction of an induced magnetic field in a loop of wire. It tells us the induced magnetic field in a loop of wire will oppose the change in magnetic flux through the loop. The experimental method for this lab was relatively simple. We determined the north and south ends of a bar magnet using a magnetometer. Then we dropped the bar magnet through a non-ferrous aluminum tube north side down. We measured the amount of time it took for the magnet to enter and then exit the tube. This was change in time. We did this 5 times. This was our experimental data. For 5 trials, we had an average time of 1.62 seconds. That means that it took the magnet 1.62 seconds to fall the length of 0.305 meters. Now, when we look at our data, we can see that it took our magnet much longer to fall through the tube than it would take the magnet to fall through the same distance in free space. The average time it took our magnet to fall was 1.62 seconds. But doing the math out, it would only take a time of 0.2 seconds for the magnet to fall the same distance of 0.305 meters in free space. That's because there's some forces acting on it that we didn't take into account. This is the theory behind what's really happening with our bar magnet and our aluminum tube. The magnet falls, producing a changing magnetic field. The magnet's velocity, the change in magnetic field, and the changing flux is all downwards. The changing magnetic field induces an EMF, as Faraday's law tells us. The induced EMF means that there's an induced current, as EMF is equal to current times resistance. The induced current will induce a second magnetic field. This second induced magnetic field will be in the opposite direction of the change in magnetic flux, so it will be upward, and current will be counterclockwise. We know this due to Lenz's law. The upward force from the induced magnetic field opposes the downward gravitational force, resulting in a smaller net downward force. This smaller net downward force means it takes longer for the magnet to fall than normal because the gravitational force is essentially smaller. Here's my code for the lab. First, we have some physical constants, mu naught over 4 pi, the resistivity of aluminum, and the gravitational constant. Next, we create our physical objects. First, the tube of aluminum foil, which we use our measured physical constants from the lab in, its length, the width. So when this code is run, this is the end result. As you can see, the magnet is falling through the tube, north side down. Taking a look at the corresponding velocity graph, we see that the velocity's magnitude increases as the force of gravity works on the magnet. However, once the magnet enters the tube right here, we see that the velocity decreases again before stagnating. This is because the magnetic force is opposing the gravitational force and causing the velocity to be smaller. But when the magnet leaves the end of the tube again, the velocity continues to increase in magnitude like it did when the magnet was free falling. All in all, this model said that the time in the tube in seconds was 3.096 seconds. This is not close to our expected experimental value, and we're going to talk about that a little bit later. Model lab questions. Which color corresponds to clockwise and which counterclockwise? In the model, the blue is clockwise and the red is counterclockwise. What happens to the dynamics of the system when you flip the magnet around? Now, if you flip the magnet around so it falls down with the south side facing down, the bar magnet's field will be going in the opposite direction, and the induced current will go in the opposite direction, and so the induced magnetic field will point downwards. This means that the net force will be the sum of the induced magnetic force and the gravitational force, which are both in the downwards direction this time. So the magnet will fall more quickly than it would in free space. Next question is, how does the total time in tube of your real-world system compare to that of your computational system? My computational system said that it would take the magnet a lot longer to fall than my real-world system did. In real time, it took 1.62 seconds to fall, and in the model, it took 3.09 seconds to fall. I think this has to do with an error in measuring the magnetic dipole moment in lab 3. The last question is, does the shape of your velocity versus time plot tell you anything about the forces acting on the bar magnet? When the magnet is in the tube, the velocity is constant, as you can see in the graph, so that means that the magnetic and gravitational forces are balanced due to Newton's second law. Conclusion. What if the resistivity of the conductor were reduced to as close as possible to zero? How would the dynamics of the falling magnet change? Ohm's law, potential difference equals current times resistance, tells us that the current would be maximized. That means that since current is proportional to magnetic force, increased magnetic force means the magnet falls more slowly. Then, what if holes or slots were cut into the tube? How would this affect the ring currents in your model? This would do the opposite. It would increase resistance, which would decrease current, and further decrease magnetic force. That means that the magnet would fall much more quickly.